Hey guys, my name is Char, and I'm going to be doing Bonding Chapter 11 for Professor Mortenson's class in preparation for the final. Let's just jump right into it. I made a presentation, so let me just share my screen with you guys. Okay. Sweet. Like I said, we're going to be talking about bonding. So to start off, let's just define it. Bonding describes how atoms are arranged spatially. So for example, what makes these two structures different? If we count up all the carbons on the left, we have 1, 2, 3, 4, and the hydrogens are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And then if we go to the right, we have 1, 2, 3, 4 carbons. And then if we go to hydrogens, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Okay. They have the same number of carbons and hydrogens, and yet the one on the left is butane and the one on the right is isobutane. They both are going to have the same molar mass because they have the same amount of carbons and hydrogens, but the one on the left has a boiling point of 30.2 degrees Fahrenheit, while the one on the right has a boiling point of 10.9 degrees Fahrenheit. Well, the reason for this is because of bonding. And if you want to know specifically why, the structures affect the bonding, or the structures affect the boiling point. Another student will be doing a video on that. Okay, what's a chemical bond? Well, it's definitely not a stick between two atoms like we were taught in elementary school. Chemical bonds are an electrostatic attraction holding two atoms close together. So just to explain this, say on the left right here we have a hydrogen atom, and that's its electron. And then on the right we have another hydrogen atom with that electron. Well, this electron right here is, well, kind of right there, is going to be attracted to this electron cloud is going to be attracted to this nuclei right there. And same thing goes for this electron cloud, is going to be attracted to that nuclei right there. So, knowing that, they are going to start coming closer together. Once this happens, we can see how there's this light blue portion that overlaps, and that is what's going to be a bond. Okay? So now the electron clouds can see both nuclei, and they're a lot happier. Just to build off of this, if we were to look at this on a graph, here we can see the two hydrogen atoms far apart. Let's just draw their clouds real quick. So there's their clouds, there's the clouds. Okay, they're getting closer, and then in this picture they're overlapping, and this picture they're like way too close. Okay, so here there's going to be a lot of potential energy, but they're going to be far apart. As they come closer, we're going to get to a point where there is a lower energy state when they're closer together. Okay, and that is going to be more favorable. To repeat, lower energy states are more stable. So the only thing to note is they can't get too close right there, or else the two nuclei are going to repel each other. Knowing this, I have a question. Is energy released or required to break bonds? Well, here, if it's a lower energy state and they're together, this area right there, then in order to get to this right here where the bonds are broken, you're going to need to put energy in that curve right there in order to break those bonds. Okay, awesome. So bonding types. The first type of bond we are going to have is ionic. Ionic bonding is a complete transfer of one or more electrons from one atom to another. So let's conceptualize this. Here, let's say we have a sodium ion and a chlorine anion. So here's going to be sodium, and here's going to be chlorine. Okay, Sodium is in the first column, and therefore it has one extra electron. Sorry, let me just make that smaller real quick. It has one extra electron in its valence shell that prevents it from being a octet, okay? Whereas in chlorine, it's missing one extra electron to create a full octet. So what's going to happen is the sodium atom is going to want to give this electron to the chlorine atom. It's just going to, it's like, I came up with this analogy. Hopefully it helps a little. But one man's trash is another man's treasure, right? And so, for example, my fiance hates olives and mushrooms. And so anytime we go and get pizza, he makes this disgusted face when it's on his pizza, but I love mushrooms and olives. So I'm more than happy to take those from him, and it both makes us happy. I know that's a cheesy analogy, but I was trying to come up with something to help conceptualize this. Anyways, so once the atom gives away the electron, it's going to be slightly positive charged because it has one more proton than it does electrons. And conversely, this chlorine atom will become negatively charged because it has one more electron than it does have protons. That will mean it's called a cation and an anion. That difference in charge is going to make this sodium attracted to this chlorine, and they're going to stick together. They're just gonna stick together. Okay? That leads us into another important topic to talk about, which is lattice energy. Lattice energy is going to be the amount of energy required to break apart the lattice, or in other words, to separate the ions. A crystal lattice is just an ordered 3D array of particles. So you know how salt, table salt, NaCl, that we use, it's like they're these little tiny crystals. It's because they're all made up of this crystal lattice structure. And so in order to break apart those bonds and make it just Na plus and Cl minus, then you're going to have to put energy into it. So that's what lattice energy is. We can use this equation right here, which is really useful, and it's just going to tell us how much energy is required to break those bonds. So we can see here that if distance is going to increase, that's going to decrease the amount of energy required. And this right here is the charge of one atom, and this right here, or I guess ion, and this right here is the charge of another ion. And so if those increase, then that's going to increase the energy required to break those bonds apart. Okay? Sweet. Next, we're going to have covalent bonding. So, covalent bonds are just valence electrons shared equally between atoms. So an example of this is going to be H2O. Here I'm going to have an oxygen, hydrogen, right? And if I draw out the bonds, we're going to have 8 valence electrons, 2 from the hydrogen and 6 from the oxygen. And so we're going to make 2, 4, 6, 8, right? Well, this oxygen right here isn't quite strong enough to completely rip off the electron from either of these hydrogens right here. So they're going to end up sharing. Okay? The analogy I thought of for this was my fiance and I both really love ice cream, but we have to end up sharing it. This is supposed to be a spoon. Because we both love it so much. Sweet. At this point, it's important to talk about some bonds are going to be, some covalent bonds share electrons equally, and some covalent bonds don't share them equally. That is what is going to create either nonpolar or polar bonds. So, for example, if we have a Cl-Cl bond right here, and we have an hydrogen bonded to a Cl right there, let me pick a different color. These two Cl, this bond right here is going to share their electrons equally because they have the same amount of pull. Whereas over here, with the hydrogen and chlorine, the chlorine is stronger than the hydrogen, so the electrons are going to spend more time being pulled towards this chlorine right here. Okay? Awesome. That means that this one's polar. Oh, sorry, this one's nonpolar, sorry. While this one is polar. Okay. This leads us to another important topic we need to touch on, which is a dipole moment. Okay? A dipole moment is a separation of electrical charge created when atoms with different electronegativities form a covalent bond. And the degree of their polarity depends on the difference in electronegativity. So here, in Cl-Cl, these would be both pulling on each other equally and cancel each other out. Whereas with HCl, the electrons are going to spend more time around this chlorine, and so the dipole moment is going towards the chlorine. Okay, that's it for covalent bonds so far. This leads me to a question. How do you determine if bonds will be ionic or covalent? Well, the answer lies with electronegativity. Okay, electronegativity, okay, hold on one second, I'm just going to pull something up real quick. Okay, electronegativity is the ability of an atom to pull electrons in a bond towards itself. So, for example, fluorine right here very badly wants to pull electrons from other atoms towards itself. Whereas atoms over here, they not so much. Okay, it has the same trends as ionization energy and electron affinity. It's going to be going to the right and up, as drawn right there. And you're going to need this table right here in order to calculate whether or not a bond is ionic or covalent. How do you tell? Well, right here it tells us that the difference in electronegative values of bonded atoms will tell us whether or not it's ionic or covalent. So here, if the difference is less than 2, it's going to be a covalent bond. And if it's greater than 2, it's going to be ionic. As a rule of thumb, this is how you'd calculate it. But basically what this one's saying is if it's greater than 2, it's strong enough to rip away that electron. Let's do some examples. So here, we're going to have oxygen. Well, that's going to be 3.5 minus 3.5 is going to be 0. So this is going to be covalent because it's less than 2. Okay. NaCl, that one is going to be 0.9 minus 3. Okay. That's going to give us negative 2.1. That is going to be greater. The difference is greater than 2, so that one's going to be ionic. Carbon monoxide, that one is going to be 3.5. minus 2.5 is going to equal 1. That's less than 2, so that's going to be covalent. And last of all, we have tin. Now, tin is going to actually lead us into our last type of bonding, which we'll talk about right now. It is neither ionic nor covalent. It is actually going to be metallic. Metallic is just going to be the communal sharing of electrons. So here we can see that this is some type of metal, and these electrons are all just floating around. And so what's going to happen is these electrons are going to become delocalized, and they're just going to end up floating around all over the place. Okay, that will make more sense when we talk about molecular orbital theory. But for now, all you need to know is that there's metallic bonds, and those are formed by metals, especially transition metals. Sweet. Okay. Awesome. Quick practice question. This was from recitation. The compound COCl2 has been used as a chemical warfare agent. It and two similar compounds, COBr2 and COI2, are all eye irritants and cause the skin to blister. The severity of the skin reactions is influenced by the polarity of the compounds. Rank the compounds in order of increasing polarity of their carbon-halogen bonds. Okay, so this just has to do with the electronegativity again. Here, it says to compare the carbon and halogen bonds. So here we're going to have our halogens, and the first one is Cl, the next one is Br, and the last one is I2. So if you want to take a second, pause the video, practice, go ahead and do that. But it's going to go in the order of least to the greatest electronegativity. So we're going to have I'll write it up here. COI2, and then it's going to be COBr2, and then COCl2. And if we want to check our answer, yep, we were correct. Okay? Awesome. The last thing we need to talk about is going to be vibration modes. This one we didn't spend a lot of time on, but basically what you need to know is that these bonds aren't just stationary. They're going to be vibrating a little bit, and they're going to be vibrating in different directions. So this one right here, I'm going to use a different color. This one right here, that's going to be a symmetric stretch, infrared inactive. This one right here, it's showing that this atom in the middle is vibrating up and down, and the ones on the outside are also going up and down. This one's going to be bending mode, infrared active, and lastly we have this one right here, where the bonds on the outside are having their bonds shortened and lengthened, and this is going to be asymmetric stretch or infrared active. That's pretty much what you need to know about vibration modes. We can also talk about how absorption of energy by atoms is it absorbs radiation if the frequency matches the difference of E of electron energy levels, and absorption of energy by molecules is the absorption of infrared radiation if the frequency matches the frequency of vibration of infrared active modes, aka it excites them. And this is the general idea behind the greenhouse effect. Okay, so that is the gist. That's in a nutshell bonding. I hope that was helpful. Oops. Okay, I don't know how to get back to Zoom. Hold on. Well, I guess I'll just end it over here then. I hope that was helpful, and if you guys have any questions, hopefully your TAs can clarify anything that I've said. Good luck on the test, everyone. Bye.